Hi, everybody. This is Gansu Yun. Thank you very much, Professor Yi, for helping me to chair the first two talks. And I'll start my role by introducing our third speaker, Dr. Sharma. He's going to talk about so-called cloaking of nonlinear plasma waves. It'll be a very interesting talk. If you're ready, would you please start?
Okay, Professor Yun, thank you very much for kind introduction. Also, thank you very much, Professor Lin, for conducting the earlier sessions and prompting us to the session. Uh, I'll share my slides uh, and please confirm if you can see my slide.
Yes, I do.
You see that?
Yes.
Okay, let me go to the full screen mode. Okay, can you see it now?
Very well. Yes.
Okay, thank you very much. So, as just mentioned by the chair, uh, the topic of the talk is kinetic mode clocking of nonlinear waves in plasmas. And this work is, let me acknowledge my collaborators first. Work is done in collaboration with Dr. Devraj Mandal and Dr. Professor Hans Schammel in Germany. Devraj has been my PhD student, and now he's a postdoc. uh, and let me also begin by thanking the organizers for calling me, asking me to give this talk and give this opportunity. And let me see if I can do justice to this. So I'll begin with first defining the terms that I used in my topic. So everybody is kind of familiar with the term mode locking. So locking is, you see a lock which locks two things together, and if generally mode locking is in that sense is locking two mode together such that they maintain a phase relationship, a constant phase relationship. You can see an example which is taken from a popular site. And as opposed to this, mode clocking that I'm talking about is, and you see the definition of clocking I've derived from Cambridge Dictionary. It shows a photograph of a clock. It's a large cloth which can clock something. It can clock a human being, a person, or it can clock a statue or something, any object. And uh, the meaning in our sense is that to cover or hide something. So what I'm going to introduce is uh, a mode which is well known, possibly clocking a large parameter space of another mode, which remains undetected for a very long time. So let us see how it unfolds. And let me show you some overview of my talk. I'll first talk about the kinetic nonlinearity, because the modes I'm talking about are nonlinear modes, and nonlinearity is generated by the kinetic effects. So it's a kinetic nonlinearity which is almost essentially present in all collisionless collective processes. And then I'll directly come to the problem of slow electron hole acceleration. So this is a well-known problem for last several years, that slow electron holes, the phase space structures, are not stable. They tend to accelerate, and we address this problem in our recent work. And then I'll come to the recent detection of stable non-accelerating ultra slow electron holes. So we could manage to go to a hidden range parameter regime in which these slow holes can be stabilized. They no longer accelerate. Then I'll come to show that how these holes can go velocity, though they are purely electron structure, they can go below the anacoustic velocity. Then I'll introduce this clocking, and then also every step I'll introduce some analytical description of them, which is derived from the theory done over last many years by Professor Shamil. So let me introduce the kinetic nonlinearity. So you know a wave, electrostatic wave, for example, is a potential structure, is a series of potential structure that can trap particles. And these trap particles are, so the trapping region and streaming regions are separated by a separatrix, which is shown in the right hand figure. And the separatrix very often tend to be an adiabatic invariant. So the time scale of change in the separatrix topology is much smaller than the time scale of change in some of the species. For example, that even ion reaction time, it's certainly slower than the electron reaction time, but it sometimes even slower than the ion reaction time. So one can see that it separates two kind of electrons, which one set is adiabatic and another set can be as thermal. So now such kind of modes, so the resultant modes, if you see a resultant wave which traps particle, is essentially a nonlinear wave. So since the number of particles trapped inside may be a strong function of amplitude, and nonlinear waves tend to be function of the dispersion in nonlinear waves tend to be function of amplitude. So these are essentially nonlinear waves, and the nonlinearity is generated by the trapping. So these are the trapped particle modes. And let us note two very important thing about these modes. The first thing is that the clocking that I'm talking about is not accessible anywhere in the linear dispersion relation, in the linear limit. So essentially the mode which mode clocking happens only in the nonlinear range in the kinetic regime. Another thing is sometimes it's very tempting to use linearly obtained results like real frequencies from the linear theory, and then try to match the results or to benchmark the results from the simulations or even from the experiments. So but it is generally very deceiving, because sometimes you have in linear theory some important parameters which are not well known, and one can always match the results. It does not mean that the real frequencies are really described in linear terms. So with these two notes, I'll go to my next slide, and you can see that what I'm talking about are very simple. Is a very simple Blasso-Poisson model. One can always go to a full set of Maxwell's equation, but here for this treatment, these full set of Maxwell's equations are shelved, and for the dispersion and stability analysis, it produces no loss of generality generally. So you can always translate the stabilities or stability analysis to full electromagnetic problems. Of course, the linear representation is a small world, but still this range, Blasso-Poisson range, is applicable to a vast range of structures which are seen in nature, especially in the space plasmas and magnetospheric plasmas, which are very close to Earth. So let me introduce these phase space structures in two ranges, okay, which we will be talking about, and one of them will be clocking the another one. So this first slide that you see here, I show our somewhat older simulations where you see an ion acoustic wave, which is almost phase velocity very small as compared to the electron thermal velocity, almost sitting at 0. So it's basically a wave traveling with the ion acoustic velocity, nearly ion acoustic velocity, and trapping the particles. So you see large trapping regions close to almost 0 velocity. It's basically ion acoustic velocity. And if you start simulations with nice sinusoidal perturbations, very soon these perturbations start trapping particles, and a solitary wave develops. And solitary wave develops because we use a periodic box. So we have to call it solitary waves. But if you use an infinite box and solitons are these wave peaks are infinitely separated from each other, this is actually a soliton limit. So both these limits are very well captured by electron hole theory, so-called electron hole theory, which is nonlinear theory for these trapped particle waves. So there are several treatments, but what we are going to follow is a treatment by Professor Devendra Sharma, and this is how the nonlinear dispersion relation looks like in this theory. So what you can see is the dispersion relation that you see in the left bottom. The only thing nonlinear about this dispersion relation is the right-hand side. The B factor or the B function is the only nonlinear function, and rest of the left-hand side is a linear dispersion relation, which everything should be very familiar with. So, and Z is the plasma dispersion function. It's defined here. So we will basically depend on this. So this is an example of solitary wave developing in ion acoustic range. Now let us go to another range. You can see that even you can go to higher velocities. So now these holes are sitting at much higher velocity on the same scale, almost 0.5 or 0.3 electron thermal velocity, and you can see that they dynamically propagate, and they propagate with a lot of solitary behavior, and they also tend to go through each other, interact with each other with very less interaction. And so this is another range. So this is electroacoustic range, but you can see that electroacoustic velocities tend to be very large. It is known that electroacoustic velocities are larger than electron thermal velocities, okay, usually. And let us see why one should be interested in these modes and this analysis. Do these electron holes or nonlinear modes participate really in the turbulence or in the operation of the turbulence? Because it is generally considered that each mode that is developing in the turbulence is developing from a very small amplitude, so it must be essentially linear. Can we have a turbulence operating with linear, non-linear thresholds? So it must be a very interesting and different regimes, and also to address with a lot of interest in the recent literature, which I'll try to show. So one can conclude what happens. So if one starts, for example, in this slide, if one starts with no trapping initially, so there are no trapped particle modes, and one can start a perturbation, and soon this perturbation will develop a trapping. So one can see that trapped particle modes are getting developed from very small amplitude of them, and then get very strong. So one can possibly decide by him or herself that whether they are going to participate in turbulence or not. Our answer is yes. So now another thing. So let me introduce this phase space hole acceleration problem. So what I show is the results from a paper from Elias and et al. PRL paper in 2004, where these holes were started from were planted in the phase space, and were started from a very small velocity or almost no velocity. For some time, they stay like this at the same velocity, at the same place. But at a very small perturbation, they start accelerating. They start accelerating and they suddenly jump to a very high velocity. And then they keep traveling with those high velocities. And if you planted more than one or two holes, one can see that they show very airy behavior. I mean, it's a behavior which was not well understood, though the paper presented it. But one can see that on the right hand side, if you started two holes, they kind of, if you try to make them go into each other, they do very strange behavior. They show very strange behavior. And in fact, they tend to trap between the non-uniformity they generated when they were not traveling. Okay, so this behavior is quite complex and could not be understood. And interestingly, it also did not receive much attention in the literature later on. Of course, there are very important and notable review papers and publications on this by Professor Hutchinson and his group, and also Sayaki et al. And there are other references that I'm not going to show here, but these are the this is our own simulation, where we could find that the slow electron holes accelerate, but faster do not. So if you already start them at a larger velocity, so in the left-hand side, a larger velocity hole started at 0.05 V thermal, and it does not accelerate at all. And in the right-hand side, you can see a hole started with slow velocity, tends to accelerate, and goes and saturates at some larger velocity. So it looks like that they don't like smaller velocities. And I'll show you possibly this movie in which you can see that this fellow tries to take off in the velocity space and tries to go and saturate it. Okay. So what is going on in the background? We tried to analyze, and we did get some breakthrough. So what we tried was, so it's the same thing, which is shown here. So our breakthrough was that we could analytically explain this phenomena of hole acceleration, at least to some extent, using a time-independent theory, which is theory by Hans Schammel. So this is theory which is actually done in the whole frame. So basically, it's time-independent theory, but we could show something. So the theory works by modeling the full phase space picture of an electron hole in the electron and ion phase space, and then one basically substitute these model distributions in Blosso equation, and goes on solving by taking some approximation and get an NDR. This is the same NDR that I already showed you. So general dispersion relation showed that there is a left hand side which is purely nonlinear. So the first term is the k naught square. So the k naught square is, as I already told, if solitons are far apart, k naught square tends to be 0. So the solitary wave has an infinite amplitude. And the second term is an electron term, is an isothermal electron term. And third term is an adiabatic ion term. And we don't know what is the term in the right hand side, whether it's adiabatic or isothermal, but it's a nonlinear term. It's a nonlinear term which appears in this nonlinear theory. Right? Depending on the model, it has a somewhat complex shape. But since we are doing simulation, one advantage we have is that we can actually recover this term from the simulation quite deterministically. So for the present simulation case, we found that if we take k naught to be finite with box size, we see that for the right hand side to be of positive sign, we see that there is a limitation on the range of values that B can take. So B can vary. Okay, to keep this term positive, B can vary only between 0 and 1.04. Okay, so it's ideally it is 1 if soliton wavelength is infinite, or it is 1.04. So 1 is the contribution coming from the isothermal electron. So we could find there is a range between 0 and this nearly 1 in which B can vary. If you start a hole which has a nonlinearity ranging in this range, then the hole is tending to be unstable and it should accelerate. So we showed it in our simulation and in our paper in 2018 in the New Journal of Physics, that we show here 3 cases in which the perturbations are started from different initial condition at different velocities, and only the perturbation that are started correctly in this red one, it tends to propagate steadily with the initial velocity. Otherwise, it goes, and then finally, if it manages to come in this range, it settles. And almost all the perturbations settled in this velocity range. So this was our first step, and we could deterministically show why the holes accelerate. So this paper that I showed you is almost 2004, and in 2018 we tried to get very close to, somewhat close to the explanation that also using a time independent theory. So we basically found a band gap in the phase space in which the holes are, and this band gap tends to be at low velocities. So you can see that at low velocities there's a band gap. So above this velocity, which is a fast velocity, which is another range of this 3.61, which is much higher than electron thermal velocity, the holes tend to be stable. So this was the first step. And then since the theory prescribed some very drastic solutions and prescribed some electron humps, we tried to explore that if we can recover the electron humps additionally. But then somewhat sadly, we concluded that electron humps are not possible because theory is a single parameter theory and possibly requires an extension, and this extension will rule out the electron humps. But there was a byproduct. Okay, we found a surprising discovery that so what we found, there are two or three things that we could see. So simulation in the extreme cases reveal the stability of very slow electron holes, though they are non-existent. So we found that since we were exploring the parameter space, we saw that there is indeed a narrow parameter space in which the slow hole tend to be stable. So they turned out, then we looked at the theory, and that it turned out to be pure balance between isothermal and adiabatic electron response only. The ion response is totally ruled out. So ions play no role. So we kind of, the EH theory had an unexplored limit. So this limit was there, but it was not even explored by the person who produced the theory as well as rest of the community. And we by chance stumbled upon it. So, so let me show. So when we did this parameterization, we went to very large Ti over T ratio. So very small T over T ratio. So ion temperature is tending to be very larger than electron temperature. Very large means 1 over 10. So 10 times larger. And we find that suitably in this regime, slow electron holes are tending to be stable. Okay, so one can see that if these holes are taking off on the top figures, but in the bottom, the hole with the same initial condition does not take off just because theta is equal to 0.1. And one can see an example. Okay, you saw the last movie in which the hole was taking off, and let me show you this movie. Looks like it will take off, but it does not quite take off. It just keeps moving. And one can see that there is indeed very negligible change in the initial profiles, fluid profiles of this. This is of course phase space. In the bottom you see the corresponding fluid profiles. So it did not take off. Then we looked at the theory once again, and to our surprise we found that if we go to very small theta limit, we have isothermal electrons and we have adiabatic electrons in the right hand side. And since theta is very small, the ion term goes to 0. One can actually treat this theory for theta tending to 0 and find the approximate nonlinear dispersion relation, which turns out to be the second term balancing the right hand side. So basically the plasma dispersion function balancing the nonlinearity. And one could see that when we do this expansion, one can now go to a linear limit of this where B is equal to 0, which means that the plasma dispersion function containing only isothermal electron going to 0, which is a limit. And one can see that one finds the classical electron acoustic velocity limit. So this is the 1.3 times electron thermal velocity. And this is where the range of electron acoustic waves starts. But when one explores a strong nonlinearity limit, which is in the right hand bottom, one can see that the V0 or the phase velocities of the hole can actually tend to 0. So VD tends to be our drift velocity, which is very small drift, because we wanted to work in the conditions where drifts are very small. They are smaller than the linear thresholds. So we found that the same expression, if nonlinearities are weak, gives you the regular electron acoustic waves, which tend to move much faster than the electron thermal velocity. But the same mode can have a velocity which tend to be much smaller or almost tending to 0. So if I don't have a drift, I can sustain a 0 velocity electron hole stably. So these two limits were recovered from the same dispersion relation. And one can now also show that same dispersion relation, if one tends to keep theta finite, recover also ion acoustic velocity. So you just expand the left hand side, and the right hand side you have B minus 1. 1 is of course the electron isothermal response, and one finds out U0 is tending like B minus 1. If B is equal to 0, one finds ion acoustic velocity. So what we concluded is that
Sharma, you have 3 minutes to.
Okay, thank you very much. I'll finish. So one tends to see that the adiabatic ion terms was actually blocking the detection of a very slow regime of operation of electron acoustic waves. So electron acoustic waves which are known to move much faster phase velocities are actually possible to have very slow velocities, which were not actually discussed anywhere in the literature earlier, and nobody could actually try to care to explore it. What is going on physics-wise? So we just looked at the physics in physics terms. So what we see is that if we have access to both electron and ion distribution functions, one can see that in the limit where theta is very large or ion temperature is very large, one can see that ions are the ion temperature is very small. One can see that ions are null Boltzmann. This is the regular limit of electron thermal, the ion acoustic waves, in which you see ion compression. But in our modes, we see an ion depression. So there's a flux balance applicable in our modes. There is no ion density excess inside. So there is no need to throw this ion. Just to avoid throwing away a lot of ion density out, the mode has to travel very fast. Okay, it has to not stay at one place such that it misses the ion reaction from that local position, and it moves away from that position such that it meets new ions, which take some more time to accelerate. And this was a physics picture. A more familiar or more simplistic picture is this. I show you this creature which is actually running on the water. And there's a big study on this. So this creature is very close to our modes. So one can see that this runs on the water, and it cannot run below a threshold speed. So it kind of acquires a phase velocity of itself. If its vertical stability, it will drown if it moves slower than runs slower than at threshold speed. This vertical stability depends on its horizontal velocity. It's kind of, it transforms itself into a wave which should have a phase velocity. So this is a creature known as basilisk lizard, and also popularly known as a Jesus Christ lizard in some part of the world. So it was very interesting to note this analogy. And then one can almost look at that by doing this, we were actually touching the regime of nonlinear subcritical instability. So we actually looked at some finer textures of nonlinear instability. Here there's a figure from a popular paper from the Diamond Group, and one can show that they have shown that there are certain instabilities which grow even below the linear thresholds. So it's very essential work. They also showed this using the phase space holes. So I come to my summary. So my summary is that the slow coherent states are possible in hot ion plasmas. The low frequency components of many turbulent spectra might be reinterpreted in terms of these nonlinear modes. So this is a possibility. This is a strong sign that the turbulence must be operating below linear threshold via nonlinear modes, since the whole activity is captured well below the linear threshold of the drifts. The stationary nonlinear structures in plasmas, double layers, etc., may also have another alternate mechanism where only electrons participate. And there may be some extra surprises in store, like who knows, I mean, if, one can see that this condition, ion having much larger temperature than electron, is well satisfied in the edge region of tokamaks, modern tokamaks. Possibly, there are certain things which may become more visible by applying this results. So I just end my case here. So thank you very much.
Okay, thank you very much, Dr. Sharma. Very interesting talk, and very well presented. And I like to ask if there are any questions from the audience. If not, I'd like to ask Dr. Sharma about the applicability of your analysis for higher dimensions. If I understand correctly, your simulation was done in 1D.
Yes.
And
yeah, of course.
So my question is whether such a stable structure in high ion temperature plasma can be possible in 3D system like tokamak.
Yeah, sure. This is a very interesting question, and in fact, this is sort of an open question. We know about the space plasmas because the structures which are electron hole structures which are clearly detected in space plasmas. Of course, they have a one dimension which is very elongated, and another dimension in which they propagate. So they are more or less one dimensional structures. But what happens to a three-dimensional structures or two-dimensional structures, like the possibility that I showed in tokamak escape of layer regime, is really to be explored. I think but the stability of one-dimensional structure, sometimes it is shown that comes into question phase-space structure if you go to higher dimensions. So one has to see if there are some hidden regimes in which they tend to be stable. So I do not have an exact answer for this, but this is to be explored. I think, yeah, this is a very nice question. But our simulations tend to be 1D, so it will take, I think, more time.
Is there any question from the audience? Then may I ask one very simple and technical question. I wonder, how do you set up the initial soliton structure?
So you mean the initial condition in
Yeah,
phase space?
Yes,
Yeah,
initial
okay.
conditions in your simulations. But
Yeah,
in,
so
in
initial
most of your simulations, it seems like you started with well-defined soliton.
Yeah, well, we have a model in which I showed in yeah. So you have, so if you actually translate this into phase space, the distribution function showed here, they are actually they have both components, free electron and trapped electrons. But we don't quite do this. We took arbitrary holes. So we take a region in the phase space where there are no electrons. So we keep some regions vacant, and they happily tend to go into the closest eigen modes, kind of closest stable structures very readily if we are in the correct regime. So this was a surprise for us, pleasant surprise, that you have to just generate a structure in the phase space very close to these initial models, need not to be exactly these initial models, and they nicely tend to propagate. So there's no spatial consideration, which is of course you have to be in the limit in which you have enough large size, otherwise they tend to be solitary waves and not the solitons.
Oh, very interesting. Thank you.
Thank you very much.
Thank you. So so we'll move on to the next speaker. But it seems like the next speaker, Dr. Jie Zhang, is not here yet. So I wonder how to proceed in this case. Shall we move on to our final speaker?
Yeah, I think we should move on to the